Yeah, so hello student, welcome to today's class and good morning. So let me start this lecture. So MA415 Algebra, okay, and okay, so this is lecture number 11, okay. Okay, today we will discuss the generalization of Cauchy's theorem due to Peter Sylow, and we call this theorem Sylow's theorem. Okay, so you remember that Lagrange's theorem tells you that order of the subgroup divides over order of the group, and then Cauchy proves that um, if we have a group, finite group, and if a prime divides the order of the group G, like what Cauchy proves. So So P divides order of the group G implies um, there exists some G belongs to G such that with order of G equal to P, right? So that means what? That is um, there exists a subgroup of G with order P, right? So Cauchy's theorem tells you that if P divides the order of the group G, then you have a subgroup of order P, right? So this is kind of partly this is kind of not full converse of Lagrange's theorem. Some kind of partly converse. So you can find out subgroups of in order P, right? The question is that what maximum you can do, and that theorem is due to Peter Sylow. So before we going to go to the statement of the theorem, so let us define some of the definition which is required. So just define this thing here first. Okay, so let me define. So a group of order any prime power, okay, order say p power r greater than equal to 1 is called a p group. Any group of order p power r is called a p group, okay. And subgroups of order this order prime power, okay, this prime, so this prime power are called p subgroups. Clear? So this is my first definition. So whenever I am saying a p group, I mean that order of the group is some p power something. And I am saying p subgroups, that means this is a subgroup of the group, and the order is p power something, some integer. Okay. So this is first definition, and then uh, definition 2. So suppose let G has order say some p power r times m, okay, with GCD of p and m is 1. So what does that mean? That means r is the highest power of p, which divides the order of the group G, okay. So then um, any subgroup, any subgroup of order this p power r, the highest prime powers which divides the is called is called a p Sylow subgroup, a p Sylow subgroup. What are the p Sylow subgroup? P Sylow subgroups are the p subgroup of highest order, okay, which divides order of the group G. Clear? Okay, so we learn what is p subgroups and what is p Sylow subgroups, okay, and then another definition we require. So I am writing that this symbol. So let me write down this symbol. Sylow PG. So this is what this is the collection of all p Sylow subgroup of p Sylow subgroups of G. Okay. So you correct all the p Sylow subgroup and then I write down this. Okay. And we use this notation. NP is the order of this. So what does that mean? So NP is the number of p Sylow subgroup of G. Okay. So this is our notation regarding this Sylow's theorem. So far, so now on we will use this notation. Okay. Whenever I am saying NP, I mean the number of p Sylow subgroups. Okay. Okay. So with this notation, so let us start discussing. Sorry. What is Sylow's theorem? So Sylow has three theorems. Nowadays we call Sylow's theorem 1, Sylow's theorem 2, Sylow's theorem 3. So let me start with oh my god, what is happening? Okay, so Sylow's first theorem. Okay, so what is Sylow's first theorem? So let us first discuss this. So what does it say? It says that so let G be a group of order say p power r into m with that GCD of p and m1, then G has a p subgroup of order p power k for all k in between 1 to r. So what does that mean? That means that G has a subgroup of order p order p square order p power 3, in particular G has a subgroup of order p power r. So what does that mean? That means this Sylow these collections of G is non-empty. So you have a Sylow p Sylow subgroups. Okay. So this implies actually the statement implies that the collection of p Sylow subgroup of G is non-empty. Okay. So whenever you have a group G whose order is p power r times n, and then G has P subgroup of every such order P power k, right? K is arbitrary, anything, okay, 1 to R in between, okay. Now, obviously, this is a very strong theorem. See, so this is more generalization of Cauchy's theorem, right? Cauchy's theorem tells you that if P divides the order of the group G, then you have a subgroup of order P, right? Here you are saying the subgroup, not only subgroup of order P, you have a subgroup of order P, P square, and even the highest power, P power R also, right? Yeah, so let us prove this. So this is more stronger than Cauchy's theorem. So proof. So the proof will be on induction. So we will use mathematical induction on this order of the group G, on order of the group G. Okay. So if this order of the group is 1, then it is trivial. There is nothing to do. Then there is nothing to do. There is nothing to do. Okay. Now we need to assume something. There is something called induction hypothesis. So what is the induction hypothesis? So induction hypothesis. What is that? So let us assume that the statement is true. Statement means the statement of the theorem. Statement is true for every group of order less than this order of the group. Okay. So whenever you have a group whose order is less than order of the group, then the statement is true. What does that mean? That means given a group, so order less than order of the group G, and some prime power, you can write down the prime power into some number, then that group contains a P subgroup of all order. Okay, so that is a statement for any. Okay, so this is so let me just prove it for K. Okay, in general. So okay. So now yeah. So what I am doing, so this P power K divides this order of the group, right, which is P power R times M, and K is what? K can be anything in between 1 to R. Okay. Now I need to prove this. Okay, I need to prove that G has a subgroup of order P power K. Okay. Now now I know that also. So we know that G is acting on this cell via conjugation, right? And hence you have hence the class equation is what? Class equation is this, right? Order of the group G equal to this order of the center of the group G plus you are taking sum over all this representative G star such that the centralizer of G is not equal to the group G, and then order of the group G divided by the order of the centralizer of G, right? And this G is actually I'm adding the star means this is sum is running over all these distinct representative of uh, the centralizer, right? You remember centralizers are actually stabilizers and they forms a partition, right? That thing. Right. And this is also same as so it's also same as the this we already proved it, right? So this is also same as the centralizer of G is not equal to G if and only if G is not equal to center, not belongs to the center. That we already proved it, right? So those are elements belong center, they are singleton class, they will be inside this center, otherwise you will have this, right? So now what happens now, there are two cases. So case one uh, okay, what I am saying. So case 1, what is case 1? So this P power K divides order of centralizer of G for some G, for some G. Okay. Then what happened? See, these centralizer of G are they are actually proper subgroup of G, right? Now, if P power K divides this centralizer of G, then what happens? Then by induction hypothesis, induction hypothesis, uh, there exists a subgroup, say H, subgroup of the centralizer of G, because centralizer the cardinality of the order of the centralizer is strictly less than order of the group, right? So induction hypothesis tells you that you have a subgroup of order P power K, and which is also subgroup of G, right? And done. So then done. So this case is done. If you have some G for which P power K divides the centralizer order of the centralizer, then the centralizer contains a subgroup order P power K, and which is also subgroup of G. So this case is done. Now the interesting case when case 2. So let this P power K does not this P power K does not divide this centralizer of G or of the center G for any G belongs to G. Okay. If it belongs to divides 1, then we already know that. Now if it does not belongs to does not divide is the order of the centralizers for any G belongs to G, then what happens? Then I have this class equation. The class equation tells you that the P power K does not divide this thing, right? So this ratio of this index of thus let me write down this index of G, which is nothing but this, right, is always divisible by P, right, for all G belongs to G. For all G belongs to G, it does not divide is the order of the centralizer, and hence this index, right? So what does that mean? That means this sum, the full sum is divisible by P, right? So thus P divides this full sum star, right? Say G not equal to G, all those disappear. Now you already know that P divides the order of the group G and P divides the sum, right? So what is the conclusion? So therefore P divides the order of the center, right? P divides the sum and P divides the order of the groups, and thus P divides the order of the center, right? Now I am happy. So I have a prime, that prime P, which divides the order of the center. So by Cauchy's theorem, there exists something, say x belongs to center, such that order of x equal to p, right? Cauchy's theorem tells us that you have a elements of order p, right? Now so you write down say, yeah, so and uh, so let your n is the subgroup generated by p. Okay, so this is cyclic subgroup generated by p, but then you see that n is actually normal subgroup G, as x is element of the center, right? This is I already proved long back ago. The central subgroups are normal subgroups, right? So we can talk about the quotient group. So thus uh, the quotient group G mod n has order say, which is order less than, obviously. So I don't order as order less than order of the group G, right? Because you have quotient out by that thing. So your order becomes less, right? So now we will use the induction hypothesis on G mod n. So now using induction hypothesis on G mod n, what happens? So we get a, see G mod n is now divisible by p power k minus 1, right? Because G was divisible by p power k, order of the group is divisible by p power k. Now p power k minus 1 divisible by divides the order of the this G mod n, right? So we get a subgroup something, say h bar of order p power k minus 1, right? Because one p is now absorbed inside this order of n. Order of n is p, right? So h bar is a subgroup of G mod n, right? And now we remember this fourth isomorphism theorem or correspondence theorem. So what does correspondence theorem tells you? Correspondence theorem tells you that there is a one-to-one correspondence between the subgroups of G mod n and the subgroup of G corresponding n, containing n, right? So by correspondence theorem, by the correspondence theorem, there exists subgroup, okay, subgroup of these such that h equal to this h bar equal to h mod n, right? that contains n, containing n, right? Yeah, so this is almost done. So you know h bar has order p power k minus 1, n has order p. Then what is the order of h? Finally, so order of h is nothing but order of h mod n into order of n, right? So this is h mod n is what? So h mod n is p power k minus 1, and this is p, so this is p power k. Ah, p power k. Okay. So thus we prove that so this completes that theorem. So we just proved that Syllow's first theorem is true. So what does that mean? That means that if G has power p power r times something, then for every prime power p power k, G contains a subgroup, and uh, and the set Sylow p subgroup of G is non-empty. So you have one subgroup of highest order. Okay. Okay. So this is that Syllow's first theorem tells us that existence of P subgroup and P subgroups. Okay. Now let's yeah, I will give lots of examples. Don't worry. So let us now try to understand Syllow's second and third theorem, which are more involved actually, and then we will uh, try to give applications and corollaries maybe in our next class. Okay, let's see. Okay. Now, what is Syllow's second theorem? So, Syllow's second theorem. So, what does it tell you? It tells you that uh, every P subgroups of G contains in content in say content in some P Sylow subgroups. P Sylow subgroups. Whatever P subgroup you choose, it will be sitting inside some P Sylow subgroup. Okay. In particular, all the P Sylow subgroups are conjugate to each other. Conjugate to each other. Okay. So what does it tell? So whenever you choose a P subgroup and a P Sylow subgroups, P subgroups, it will be sitting inside a P Sylow subgroup, and whenever you choose any two P Sylow subgroup, they are conjugate, right? Conjugate to each other. Now, yeah. So these theorems requires this is non-trivial theorem, so you need to understand properly. Okay. So start with the proof. Okay. Okay, so we know that P Sylow subgroup is a collection of P Sylow subgroups non-empty. So let me just start with this. So let X be the okay. So um, uh, No, so let me start with one Sylow subgroup, right? So and then I will come to that. So let P, capital P, be a P Sylow subgroup of G. Okay. Now consider this set, say X, which is what? Which is the conjugates of P. So G inverse says that G belongs to G. So we already know that G inverse are also subgroup, right? That we know, and they are also P0 subgroup because they are the highest order subgroup, right? So P is a P0 subgroup means what? So that means that order of P is that small p power r, the highest order. Okay, and we consider all the conjugates of this, right? Okay, and now I need to prove that any P subgroup is contained in some P subgroup, right? So now let you start with some H be any P subgroup. Any P subgroup of G. So you start with any P subgroup. What does that mean? That means order of H is some prime power. Okay. Clear? So now see that this H is acting on X via conjugation. What does that mean? That means you choose an element of X. So that is this. We have a map from H cross X to X by this kind of this H dot. So element of X are some conjugates, say Q, and you have, this is nothing but H Q H inverse, right? This is that group actions. Okay. So you check this. So check that. This is okay. Group action. I think we already checked this kind of thing, right? So H contains H acting on V. X, what is X? X is these conjugates of this P Sylow subgroup P. Okay. Now question is that, now this is a very important question. So what is about H invariant elements of element of X, right? So this is fixed set of H. What do you know about this thing? I mean, we know that this cannot be non-empty, right? It's always there will be always an element that you already proved. So now let you choose an element, say Q, that belongs to this fixed points of H. So what does that mean? That means that H, that is what does that mean? That means H Q H inverse equal to Q for all H belongs to H. This is the definition of fixed one, right? For these conjugation actions, right? Because H dot Q is nothing but H dot Q is nothing but H Q H inverse, right? There has to be Q. So what does that mean actually? That means if every element of H normalize Q. What does that mean? That means H is actually subset of normalizer of Q in G, right? Every element of H that normalizes that full set Q. Okay. So this is so far this is okay. Now my claim, if this is true, this is my claim. H is also sitting inside Q. This is my claim. If I prove that, I am done, because I know that Q will be what? Q is some conjugate, right? Q is nothing but some G P G inverse for some G belongs to G. And if H is sitting inside Q, that means H is sitting inside some P star subgroup, right? So this is the claim actually. Now how to prove H is sitting inside Q, and the Q is nothing but the H invariant points of X. Okay. Now how to prove here? So let us prove by contradiction. So if not, then then there will be maybe then there will be some X belongs to H which is not inside Q, right? So I want to prove that H is sitting inside Q, is a subset of Q, and I am assuming that it is not true. What does that mean? That means there will be an element of H which is not inside Q, right? Now if we have H which is not inside Q, then what happens? So then you check that these cosets of X cosets of X and Q, this is not equal to Q, right? Because X not inside Q, the coset is not inside Q, right? Then this is not equal to this. But you know that Q is normal inside normalizer of Q, so I can talk about this group. So this group has order. What is the order of this group? See, Q is, what is the order of Q? So let me tell here. So here you can see that order of Q is the highest order, right? Order of P, which is nothing but P power R. And you are quotiented out by the highest order of P. So what is remaining? The remaining part will be, so this order divides that M, right? Where this P and M are co-prime. Remember in the beginning we started with P power R into M, where P and M is co-prime. So this order has order which divides M, right? Yeah. So what does that mean? That means order of this group is co-prime to P. Okay, this CD is 1, so this order, right? So this is okay, this okay. So if you understood this part, so let me now take this element also again, AGIN. This cosets is an element of this group, this quotient group, right? So similarly order of these the something like down K, that is co-prime to P, right? Because order of the whole group is co-prime to P, and you know that order of the element is divided the order of the whole group, so there cannot be any common factor with P. This is okay. Okay, but what is the meaning order of this? So this means that x power k q equal to the identity, which is nothing but q, and hence x power k belongs to q. That we already know, right? Order of this means x power equal to k, and GCD of k and p is 1. This is also you know, right? But GCD of kp1 also implies that any power of, so let me come later. So let me just tell one more thing here, then I will. So this one is okay. So order of these the coset of x in coset of q with respect to x is coprime to p, and if it is k, then x bar k is element of q, right? So again, also as x belongs to h, and h is a p subgroup of G, we have what we have, order of x is some prime power, right? Because order of x equal to some, say, p power p for some integer, okay? Because order of x divides order of the group h, and h is p subgroup, right? So again, so what we can conclude? We can conclude that k and p power b GCD 1, as k and p is 1, right? P is a prime number. So if p does not divide k, then p power any power b does not divide. There is no common factor, right? So using you remember that Bézout lemma. So you remember the Bézout lemma. So what does the Bézout lemma tells you? That tells you that thus there exists k1, k2 belongs to z integer, such that what happened? K1 into k plus k2 into p power b will be equal to 1, right? Bézout lemma tells you that, and so x will be equal to x power k1k plus k2 into p power b. So you can write down as x power k power k1 into x power p power b power k2, right? But we already know that order of x equal to p power b. So this is 1, this is identity. So we will have x power k power k1, right? But again, we know that x power k, you check, x power k belongs to q. So x power k1 also element of q. Q is closed under multiplication, right, product. So what does that mean? That means x is an element of q. But this is a contradiction. We started x which is outside q, right? So this is a contradiction, and thus H is a subset of Q. Clear? So understood. So you have you find out that whenever you have a P subgroup, that will be sitting inside the P cell subgroup, some P cell subgroup, and which is some. Okay, so this is something. Okay. G P G inverse, right, for some G. So every P subgroup is sitting inside some P subgroup. So this is the first part of the theorem what I proved, that what we want to prove, that P subgroups are sitting inside some P subgroup. Okay. Now the second part, that every two P subgroups are conjugate. So that part we need to prove. So in particular, if H belongs to this special subgroup of G, then what happens? The order of H will be So again, so this also, if H belongs to Sylow subgroup, then H is also a P subgroup, right? So the whole game you can again play, and you can say that H is sitting inside uh, some conjugates of P, and not only that, order of H is same as order of P, which is same as order of GPG inverse, right? Order is also same, and there is no other option. It has to be equal to this GPG inverse, right? So every two Sylow subgroups are conjugate to each other. So if you choose any Sylow subgroup, there has to be some GPG inverse for some G, yeah, obviously, for some G belongs to G. Okay. Yeah, so I think I should stop today's lecture, and third theorem we will discuss the next lecture. Okay, because this will be now be getting probably too heavy for you guys. Okay. Yeah, so let us conclude this thing.